an honor to have this special seminar by Smeenk. He will talk about dark matter, how to measure it. So,
perfect. Thank you. Thanks so much for the invitation to come. I'm testing my coherence time scale, given that I just flew in this morning. So I'm hoping that it's longer than 45 minutes. We will see. So this talk is a sort of combination of advocacy for an approach to issues in general philosophy of science, where we take measurement as central, and then thinking about that as applied to dark matter. And so this is a blob diagram from a paper by Antonius, which what it characterizes is all the potential ways we could try to observe dark matter as it's been proposed. And of course, one of the striking things is that all of the really systematic and convincing evidence for dark matter only comes from this part of the blob diagram. In essence, its cosmological and astrophysical implications. And so one of the things I'm interested in is seeing if we can run a kind of coherence argument for dark matter on the basis of this group of different lines of evidence, much like we've run for things like the existence of molecules in the early 20th century. And so this is one example of a list. So Katie Mack is an astrophysicist who's at the Perimeter Institute. She gave a talk where she listed, I think you might see some variations in this list, but this is her attempt to list all the 13 distinct lines of evidence from astrophysics and cosmology that provide some information about dark matter and its properties. And what I'm interested in is how strong is the kind of coherence argument based on looking at these, granting that we have essentially nothing but maybe upper bounds and things like that from these other sources of evidence we'd be interested in pursuing. There's a common historical narrative that I think Peebles sort of spells out quite explicitly, but I think it's not unique to Peebles, that there's actually an interesting shift in the evidential status of the lambda CDM model, and in particular, one of its main components, the claim that there's a substantial contribution from cold dark matter. Peebles says that in around 2003 to 2008, there was a revolution in cosmology where this became much more well established. And so one of the other interesting questions is what sort of shift in the evidence was important at that time that led him to think that this is an important transition. There's a more detailed, I'm not going to be doing a really detailed historical discussion here, but there's an interesting kind of question. Is there a shift in the nature of the evidence for dark matter that's similar to other shifts in evidence that we've seen in historical episodes like the early 20th century and the case for molecular reality? But of course, Peebles also acknowledges, he says, even though there's been this shift in the status of lambda CDM, there's dark clouds, and he identifies the second dark cloud on the horizon. Here he's explicitly referring back to Lord Kelvin's discussion from the famous Baltimore lectures, when at the end of the 19th century, Kelvin identified dark clouds on the horizon of physics. Peebles' second dark cloud is what he calls the enigmatic simplicity of the dark sector. So it includes both dark matter and dark energy. So he's acknowledging that despite the fact that he thinks there's been a revolution in the evidence in favor of lambda CDM, there's definitely open questions. So the things I'm interested in this talk.
Sorry, Kevin.
Yeah.
Does he spell out what he means by simplicity?
Not really. I think it's just that we don't know much about dark matter and dark energy beyond their cosmological implications. And that it's sort of, we don't know any detailed structure of dark matter. I forget what he said explicitly, but I think that's right.
Yeah, I think a lot of people use simplicity as well, but presumably in a very different.
Probably a very different way, yeah. So the philosophical questions I'm interested in pursuing then are, first, the question about evidential reasoning. So what if we take theory-mediated measurements as one of the key ways that we gather evidence for a theory? And when we do so, what's the convergence of multiple independent lines of evidence contribute to the evidence for a theory? How strong is that evidence? How compelling is it? And then, relatedly, in what sense does evidence of this kind support realist commitments? And in particular, in this case, to dark matter? And what does this commitment amount to? And I'll be saying a little bit closer to the end about some of the relations to recent work in philosophy. There's been a lot of philosophy recently looking, Niels is one of the people who's contributed a lot to this literature, but there are other people as well who are looking at how to consider the case of dark matter, both in terms of the competition between dark matter and other alternative models in physics, and also in terms of how to think of it as what kind of realist commitments we should have to dark matter. Okay, so in outline, the first two sections are more setup and looking at a historical case study that I think is quite useful. And, or sorry, the first 3 seconds, and then three sections, and then I'll be turning to dark matter more specifically in section 4. So to be clear, this is an approach that I'm really influenced in adopting from George Smith. So there's work that he did on Newton's methodology, the classic paper Closing the Loop, and then he also has a book co-authored with Rajev Seth, which is a detailed study of evidential reasoning in the case of Brownian motion and molecular reality. And there's a few things that Smith does that I think are really quite important and interesting in reconstructing the evidential reasoning in these two cases. So I'm going to be focusing on the case of Brownian motion here because it's closer to the questions I'm pursuing. And overall, the focus is, he's interested in shifting the focus to evaluation of theories to long-term evaluation, sort of long-term progression of theory over decades or centuries, and how it can be used iteratively to give a more and more detailed account of some target set of phenomena. And part of what's going on in supporting this iterative approach is we want to gain access to novel quantities or entities. Typically, our theories introduce new ways of describing the target system. We introduce new quantities, and those are useful then in giving us this a new description that supports this iterative procedure. And what I mean here by lower level principles is that if you actually look to see what is relevant for gaining access, it's often a fragment of theory or a piece of theory rather than an entire theory that allows you to gain access to a new quantity. And once you've established that access, that enables further research. So it plays a constitutive role in enabling further research. And Smith ultimately argues for the permanence of some results when we have a kind of successful series of theory-mediated measurements and successful iterative development. And the argument is both tracks a weak dependence on fundamental theory. So we often are able to understand how this approach works without being committed to anything like a comprehensive theory. It's more that we have individual principles or parts of theory that are relevant for the reasoning. And also that when we're doing an iterative process, we're often employing counterfactual reasoning based on the description we have at hand. And the success in using that counterfactual reasoning gives us confidence that something about the theoretical description is physically significant. It's mapping something accurate. So this focus on measurement, there's another literature that's developed in philosophy of science in which Hasek Chang and a number of other people, Aaron Tall more recently, have really focused on measurement as an interesting question in general philosophy of science. And so I think that my approach is partly inspired by that work as well. So what do I mean then by theory-mediated measurement, and how does it play an approach in this iterative kind of account? So very, very schematically, what I mean by a measurement of some target quantity is just that we have a theory that gives us a dynamical, this is, very schematic, that we have a dynamical coupling between an instrument and a target system of interest, such that there's some functional dependence. So we have something like a pointer variable on our instrument that tracks some interesting quantity in the target system. Notice that the assessment of whether you can actually perform a reliable measurement is going to be based on your theory, your description of this functional dependence. So to say I have a reliable measurement instrument is basically based on the dynamical description you're giving that links an instrument to the target system. So it's internalist in that sense. It's presuming some theory that describes both the target system and the instrument you're using. And it really just acknowledges that theories are ampulative. Once we have a theory in place, we can use that theory to gain access to quantities that were otherwise beyond our reach. And so measurements and experimental design just exploit our understanding of theory or fragments of theory to amplify quantities of interest so that they're accessible to us. And we say that we then have a successful measurement practice if the approach yields the following kind of features. So, I want to access new quantities. These quantities are useful in describing physical systems. So think very, probably one of the first cases of people using this kind of approach. So my Dutch ancestors will be ashamed that I can't pronounce his name, but Christian Huygens. Okay, thank you. Was probably the first to introduce theory-mediated measurements in a really sophisticated way. So here's an example of the features of theory-mediated measurements that lead to thinking of it as a successful practice. So he was interested in measuring the time of free fall using a variety of different pendulums, and also just understanding how to do precise time measurements with pendulums. And so he famously introduced the cycloidal pendulum, in which the pendulum bob moves along a cycloid, so it's a true isochrone. But he also introduced other kinds of pendulums. The one in the figure here is a conical pendulum. So it's a slightly different physics, actually, describing how this pendulum works. But we can ask, is there stability? So sorry, first of all, stability would just be if you measure it with pendulums of the same type, do you get similar answers for the acceleration due to gravity? In convergence, you'd be interested in using a conical pendulum as well as a cycloidal pendulum. You can also try doing direct measurements of free fall. Those are much trickier because it happens very fast, right? A convergent measurement would be agreement of measurements of different types. And so if you first have stability, then you have some sense that you're tracking a real quantity. If you have convergence, then you have different ways of tracking that quantity that depend on different aspects of the theory. And you typically also demand, importantly, that as you increase the precision, you can maintain this level of stability and convergence, right? And so if you have a theoretical understanding of the system, you can identify and control the kinds of error that would arise so that you can increase your precision systematically. And so successful measurement practice means that we want to maintain stability and convergence under steadily increasing precision. All this seems, I'm sure, really straightforward, right? This is a simple example. But the further claim is that the principles involved in a successful measurement practice, so whatever it is, the physics that's employed in the measurements of the acceleration due to gravity here, or whatever other quantity it is that you're targeting, the claim that Smith and Seth make is that when we have successful measurement practices, the determination of the lower level principles through theory-mediated measurement can lead to results that are taken to be permanent, in the sense that they survive transitions to new, more comprehensive theories. So whatever the elements of theory are that are involved in these measurements, we would expect them to be preserved in the next theory. And in fact, this was the case. The way Huygens was describing this was really within the context of a Galilean description of gravity. But Newton actually shows that even with the transition to the full description of gravity in the Principia, these results can be preserved, right? So the way you understand the measurements is then preserved even though you've changed your theoretical understanding of gravity. And so the claim is then that if we understand the content of the theory in terms of the degree to which it supports successful measurement practices, we can identify what it is that's playing a role and take that as being something that we should preserve in future theories. So, yeah.
So by this example there, so which theory is being mediated?
The theory of the description, the description of bodies in free fall under Galilean gravity. And so what I'm saying about what is preserved, so under Galilean gravity, you just think of the free fall, the force of gravity has been directed along parallel lines, right? When you actually move to actually a centripetal force of gravity, then the description of gravity is different, but you can recover the reliability of the pendulums as an appropriate limit. So the claim is it's not always going, so it's usually going to be a fragment of the theory that's relevant for the particular measurement. And the point is you should analyze the measurements to see what are actually the relevant bits of theory that connect, say in this case, G to the way the conical pendulum works, or G to the way the cycloidal pendulum works, or G to freely falling bodies. In this case, it's relatively straightforward. It's just a description of freely falling bodies overall. Okay, so the point is that this is a relatively rich description, right? If you're giving me a theoretical description of these measurements, it's counterfactually rich. in order to understand how these measurements are reliable. And so it's a fragmented theory. And insofar as you have a successful measurement practice and you want to preserve that, you're going to require a subsequent theory to sort of recover that fragment of the theory that's relevant to those successful measurement practices. Okay, now I've just really quickly sketched this approach to think about the content of theories in terms of what kinds of measurement practices they support. And let me turn now to a case study where Smith and Seth in particular have focused on how we can make inferences on observables and clarify the different aspects of evidential reasoning in the case of molecular reality. So again, this is probably fairly familiar. Around 1900, I think it's fair to say that the physics community regarded the molecular hypothesis as something like an interesting hypothesis, but they would have probably said that it was a mere hypothesis. And the determinant, so in order to determine molecular properties, there were a number of assumptions that had to be made that were quite implausible. For example, the sphere of influence was you actually had a sphere with a definite radius, and then you could use that to determine other properties to try to understand the molecular scale properties. But these all seemed very model dependent. They seemed to rely on some very implausible or speculative assumptions. And when people tried to determine these molecular scale properties using these different types of results, they didn't really lead to stable and convergent results. So they didn't lead to stable estimates of molecular scale properties. But in a fairly short amount of time, there was a pretty dramatic transition. And this is, there are a number of quotes that you could find. Ostwald is interesting because he was one of the critics of the atomic hypothesis early on, and he really thinks of it as making a dramatic transition by 1915. So what is it that happened during this period? I'm going to go over this very quickly. The one that's most famous, of course, is precision measurements of the mean kinetic energies of granules in Brownian motion by Perrin. It turns out that there were a number of other precision measurements that were all complete by around 1911, all of which had the following feature. They were based on relatively plausible and straightforward assumptions linking the quantities that were measured to molecular scale properties. So unlike what was present earlier, in these cases, there is a fairly plausible linking assumption that was all that was required in order to make this inference. So what we have then is a set of precision measurements where there's some kind of theoretical hypothesis providing the link to molecular scale quantity. And what we see, so in the case of Brownian motion, again, I'm going over this fairly quickly, but I assume it's familiar. We have the link provided by the assumption that the mean kinetic energy of the granules is equal to the mean kinetic energy of the molecules in the fluid, where by molecules, we really just mean localized, discrete, independent pressure fluctuations. We don't have to mean anything more than that. And then we get an estimate of Avogadro's number, granting that linking assumption, right? And the feature that I want to emphasize is that this is a really thin concept of a molecule that's relevant here. Yeah, Neil sees what's coming. So there's really no commitments regarding the shape, the internal structure of the molecule. This is all before the development of quantum physics, right? Well, quantum physics was underway at this point, but we didn't have a quantum description of the internal structure of the atom. But that was actually not relevant for this analysis. What was relevant is just that it's a localized independent pressure fluctuation in the fluid. And so this is really just a partial account of what a molecule is that allows for this link between some observable property and then a molecular scale property that you're targeting. And this is true for each of these different lines of evidence that I mentioned. And the other point is that this is in some ways independent from a full theory. So it employs one aspect of statistical mechanics, but it's not actually a comprehensive theory of molecules. It's assumed in order to have this link between the molecular scale properties and what you can observe in the case of Brownian motion. Now, I'm not going to go through each of these links in detail, but I mentioned that there are 4 different lines of evidence that were really important as of 1911. And what does the convergence of measured values contribute to the case that this is a permanent understanding of molecular scale reality? So we have 4 different ways that were then available as of around 1911 to count Avogadro's number. And also there are other quantities. I'm simplifying a bit by just focusing on Avogadro's number. The one that I mentioned before is the most familiar, but there are a number of other ways that were associated with those other 3 lines of evidence that all also gave you an estimate of Avogadro's number. And it turns out, and there are more qualitative results, like Perrin mentioned another, I think he had 13 total different ways of estimating Avogadro's number. The others weren't nearly as precise as the 4 I've emphasized. And what do we have? In each case, we have a substantive ampliative linking assumption that involves some aspect of molecules that allows you to link the experimentally accessible quantity to the Avogadro's number. And the agreement and the distinct determinations of Avogadro's numbers provides mutual support for this set of linking assumptions, and it gives you a fuller conception of molecules and how they're how these different properties constitute molecules. It's still a partial conception of molecules, but you get an understanding of different aspects of molecules through these 4 different links. It turns out, except ironically for Perrin's own measurements, they were off systematically by about 10%. Smith reports that it's still a little bit unclear. It's probably some subtlety related to viscosity that wasn't fully understood. So Perrin, even though he was the one who made this convergence argument most famously, it turns out his own measurements were the outlier. And so then we have, and the final important point is that the value of Avogadro's number and the other constants that were determined by these kinds of arguments really played an important role in the development of quantum physics, because for Bohr, for example, in calculating the spectral lines, he has to have values of these constants in order to compare the model he has with actual observations. So having these values is actually something that allows you to make the next step to pursue the further inquiry into the nature of atoms and molecules. And this quote from Poincaré, I think, really emphasizes 2 points that are crucial here. The first point is that he's emphasizing the value of the convergence. He says, the brilliant determinations of the number of atoms have completed the triumph of atomism. I won't read the whole quote, but then he also acknowledges at the end, and yet each new discovery in physics reveals a new complexity of the atom. So it wasn't that these determinations closed off inquiry or closed off our understanding of the atom. In fact, it opened them up. And the understanding that we had of the molecular scale properties helped to determine constants that were feeding into the development of quantum physics. Okay, so that was the warm-up case. And now I want to shift over and look at dark matter. So the guiding questions then, so I'm interested in applying this sort of general approach, thinking in terms of the content of a theory hashed out in terms of what measurements it supports and whether we have successful measurement practices that give us access to quantities. And I'm applying that framework to the case of dark matter. And here are 3 of the guiding questions that we'll be looking at. So the first is, how much convergence do we have versus how much should we expect in the future? So are we looking at the actual case for convergence versus are there prospects for further lines of evidence that will converge in the future? To what degree do we have different features that we can see as converging and determining a sensible sort of core concept of dark matter? And especially when we're looking at methods that constrain quite different properties of dark matter, how do these convergent lines of evidence support one another? And finally, how strong should any realist commitments be given the evidence? Should we think of dark matter as a permanent contribution in the way that Smith argued we could see molecular reality as being a permanent contribution as of around 1913? So these are the guiding questions. And I should be clear, this is in some sense also more perspective. Like this is, I think, an interesting way of approaching this set of questions. And it's not something that I've completed the analysis of, but I'm going to sort of give you more gestural ideas about how to approach these questions from this point of view.
What's the link between model and realism? Do you take them to be synonymous, or model commitments imply realism, or the other way around?
So it's partly, I think of it as very closely related, but what I mean by modal commitments is something like the modal profile, like how is it that we characterize dark matter? How does it fit into different explanatory or predictive accounts, right? And so your modal commitments, you might still be an anti-realist and have something like that. So it's yeah, it's a bit subtle, but I'm thinking of it as closely related. So, and that's maybe something we can discuss again. So, so the project then, so I mean, I'm taking Katie Mack's list just as an indicative list. Again, I think this is the kind of thing that you could find survey articles that give, or review articles that give similar lists of the different lines of evidence. And so the project then, which again is something I've started, but this is not a report on the final results of it, to look at this in much the way that Smith and Seth looked at the case of molecular reality. In each case, what is measured? How is that measurement linked to the properties of dark matter? What are in fact the properties of dark matter that are relevant for that kind of measurement or that line of argument? And, you know, given the kinds of linking assumptions in each of them, to what extent do those linking assumptions provide support for one another through a kind of coherence argument, insofar as these all converge, right? So there's also just the prior question, to what extent do these actually converge and determine properties of dark matter that are consistent among all these different lines of evidence. And so this is, I think, just restating what I was saying a moment ago, that we would ask them, do dark matter measurements exhibit the pattern that we've seen in other kinds of successful measurement practices in the history of physics? Is there stability? Is there agreement among measurements of the same type? Is there convergence? Is there agreement across different measurement types? And how are the linking assumptions related for each of the 13 different, or there might be more, but the 13 lines of evidence in Katie Mack's list? And is this level of stability and convergence maintained as we've had increasing precision? So, for example, Peebles emphasizes that one of the things that happened in the early 2000s is that we started to have increasingly precise measurements from the CMB and other sources. And he thinks that we started to have, we sort of maintained convergence on understanding the properties of dark matter, even as we had increasing precision. So if that's the case, that also gives us some evidence that we have a successful measurement practice.
If we keep measuring rotation curves, that's not convergence, that's stability. That's
stability, yeah. So if we get the same profile, so if we get the same density profile with rotation curves and, I don't know, stability analysis of spiral galaxies is more theoretical. But if you get the same you know, the same halo profile from a different method, then that would be convergence as opposed to stability.
Same profile as in absolute parameters.
Yeah, yeah. Okay, so so I'll give. I mean, this is probably unnecessary for this audience, but just to give you a sense, so you know, the goal would then be to go back to this list and do the following kind of analysis for each of these cases. Right. So in the case of Big Bang nucleosynthesis, this is one of the commonly cited constraints on dark matter. What is in fact measured? What is it that we're using as our measured outcomes? Well, it's the primordial abundances of the light elements. There's still a lithium problem. So there's an anomaly here that is not yet resolved. Those are measured from things like quasar absorption lines, looking at really metal poor stars and so on. To link that to a claim about dark matter, we first have the nuclear physics of light elements and how those nuclear reactions take place in an expanding universe. And if we make the assumption that there's no exotic physics during the Big Bang nucleosynthesis epoch, then we get a tight constraint on in particular on the baryon to photon ratio. How do we get an inference to dark matter from this? Well, if we have an independent measurement that says the total matter density is greater than this. So what we really get is a constraint on the baryonic matter density from Big Bang nucleosynthesis. If we have other reasons to think that the total matter density is a lot greater than that, then we have to say that there's something else present. So this is really a kind of indirect argument for dark matter. What you're really doing is constraining the total amount of baryonic matter. If you have other reasons for saying that the total amount of matter, the total matter density is higher, then it has to be non-baryonic. Right? So this is really, what is the inference here? It's a constraint on dark matter that there can't, so it can't participate in these nuclear reactions in the early universe, so it has to have these sort of limitations. on its features. So, so in each case, then the goal is to go through, and again, this is the kind of thing that has been done in Astrophysics Review articles. So it's really just sort of synthesizing what is the physics that is involved, what is actually the constraint on dark matter, and what physics does it depend on, right? So this would be then trying to identify as sharply as possible the kind of linking assumptions that are the analog of the linking assumptions in the case of molecular reality. And so the further claim that Peebles makes is that the ones I've highlighted in red are really the more recent types of measurements that give constraints on dark matter. And his claim is that really the reason why there was a revolution, as he describes it in the early 2000s, is that there was, with these higher precision measurements, there was then an ability to see whether you'd have maintained stability and convergence even as you increase precision. And so, for example, probably the most important of these is the CMB acoustic peaks. And here, again, this is probably familiar, but what we're seeing here is the angular power spectrum for temperature fluctuations for the small anisotropies in the CMB. And this really depends on understanding the expanding universe models, the FLRW models, and perturbation theory, and plasma physics to describe the baryon photon fluid dynamics. And then once you've done that, you get inferences about the nature of dark matter, that it has a direct impact on the photon baryon oscillations, and that leaves an imprint in the pattern in the CMB spectrum, and in particular in the relative amplitude of the peaks. And so you get both an estimate of the total matter density and separately an estimate of the baryonic matter density due to damping, and so that is reflected in the relative amplitude of the first and third peaks. So again, given a lot of assumed physics in the background, the FLRW models, your understanding of plasma physics, you get a direct estimate of the total and baryonic matter density that allows you to infer that the difference must be due to dark matter. And again, what is it that you constrain on dark matter? It has to be collisionless, I guess dissipationless as well, so that it doesn't participate in the baryon photon oscillations. Okay, so these lines of argument are the kind of thing that Peebles has in mind. This is a quote from an earlier paper in 2015. This is also the kind of argument, he just said a little bit cleaner here than in the 2020 book. He says, I'm deeply impressed by the variety of independent lines of evidence that point to LCDM and conclude that the case for LCDM as a useful approximation to reality on the scale of the Hubble length is about as good as one gets in physical science. And so really, it's the argument that he's putting a lot of emphasis on is a kind of convergence argument, that we have an agreement in the measured density of dark matter. Here I put it as a ratio of baryonic to CDM across various measurement techniques. He has reviews of these in both the 2015 article and the book. And another, this is just to emphasize that there's a separate argument that he gives, which is really also the role of dark matter in structure formation models. Right? So once you've accepted dark matter, the standard model has been, they've developed an account of structure formation based on including dark matter as an absolutely essential ingredient in that account. So obviously there's further work here. So as I said, this is somewhat prospective. I really think it would be worthwhile to do a more thorough assessment of the linking assumptions and different aspects of physics relevant for each method for all of these different 13 lines of evidence, and also to assess the precision that they've been able to achieve. And to look also, this is a more historical question, at whether Peebles's description is something that's widely shared in the community and also justified by the changing evidential case that was available to people working in cosmology. So again, this is, I think it's plausible that Peebles has described this well, but I think it'd be interesting to look more carefully to see what was really contributing to that sense that there was a big improvement in the evidential case for dark matter as of that time. Okay, so now let me compare this to the molecular case. Again, using historical analogies can be problematic, but I think in this case, the molecular case is just such a wonderful example of the strength of this kind of convergence style reasoning. So I think it's useful to see how it compares for that reason. So in terms of the similarity, again, we have distinct linking assumptions. So different aspects of physics are required to connect observations to quantitative features of dark matter. And also, once you've proposed and constrained features of dark matter, it supports further inquiry and leading to accounts of structure formation. And it turns out that what the features of dark matter that are needed in cosmology and astrophysics are really just bulk properties. You know, what does it have in terms of an impact on large scales in terms of the formation of structure? But it doesn't have as much to say in terms of the sort of the nature of dark matter as it might feature in a theory of fundamental physics. So, so we can then ask the question about permanence by asking, to what extent have the measurements achieved permanence? Is there a reason to think that the current picture of lambda CDM would survive theoretical transitions and support and constrain ongoing research? And I think here there's a big asymmetry between two different aspects of dark matter. I think there's a really strong case that cosmological bulk properties of dark matter, you can, I think, make a strong case that those are permanent in the sense that I'm using that word. They do seem to be foundational for lambda CDM, for our account of structure formation, our account of precision cosmology. So you have to imagine a very different cosmological model in order to be able to sort of unravel all those lines of reasoning. On the other hand, we really don't have much to say about the properties of dark matter identified as a particular type of particle, for example. We have exclusions, we have constraints on whether it can interact electromagnetically or via the strong interaction, or how much it can interact via the weak interaction. But we have a huge proliferation of different models that are compatible with those constraints. And we have a lot of detection efforts that have, as far as I know, anybody can correct me on this, as far as I know, have still just yielded upper bounds. So there are then disanalogies with the molecular case that are quite striking as well. So we have these constraints on properties at different scales, convergence on bulk properties. But this leads to the question, can a concept be too thin? So, and this is something that Niels has been concerned about as well. We have, in some sense, a functional role that we need something that plays this particular role in terms of its bulk properties, but that's compatible with a huge variety of proposals for a particle physics source of dark matter or other candidates like primordial black holes. And so we have, in some sense, asymmetric support for ongoing inquiry in cosmology versus particle physics. And so this goes against some of the hopeful rhetoric about unification of particle physics and cosmology in the early 80s. I think in this case, it hasn't been as clear how to learn about fundamental particle physics from its impact on cosmology, even though cosmologists have made a lot of progress in saying, for something like the Standard Model to work, here's what the properties of dark matter would need to be for us to have a viable account of structure formation compatible with all these different lines of evidence. So, does the current state of dark matter evidence warrant any kind of realist commitment? So I've been focusing more on the kind of arguments that the advocates have made. So this is the kind of thing Peebles mentions, the multiple independent techniques, convergence on key parameters. It might be thin, but it characterizes the features that are relevant for cosmology. Arguably, there's no viable alternative. This is arguably, I put that, I'm setting aside here debates about Mond. I can come back to those in the Q&A if people are interested. But again, this is, I think, the sort of common position in cosmology that there isn't a viable alternative theory of gravity. And it's clear, absolutely clear, that dark matter is indispensable for the Standard Model and for the account of structure formation. The skeptics, on the other hand, emphasize a few important points. One is that the convergence is incomplete in the sense that there's, it's not clear how tight the connections are among the distinct quantitative properties that are relevant for these different lines of evidence. That's something that I want to investigate further, but at least it seems plausible that the convergence is not nearly as tight as in the case of molecular reality. Furthermore, we don't have any direct access that is not mediated by some assumptions about gravitational theory or cosmology. Right? So this raises the worry that perhaps we have made a mistake in our gravitational theory and that would undermine these inferences. I think that's actually harder to fulfill than it sounds at first, like finding a way to change all of those different lines of evidence by modifying gravitational theories such that you get rid of dark matter, I think is actually quite a bit more challenging than it might seem. And then finally, I think there's also, it is right that the evidence is thin, it's limited to bulk properties, and you might think that that's not sufficient to characterize the full entity, right? That we haven't given an account of dark matter because all we've done is characterize its cosmologically relevant properties. And that's where the questions about realism really come in. And I think here there's a variety of intuitions that I think the different philosophical positions reflect. And partly I just want to close by saying the way I'm approaching things, I think, leads to a different way of thinking about these debates. And I'm hoping that that might be a useful alternative way of thinking. So with the fear of trying to summarize various positions in one line, here's an attempt to summarize some of the positions that are in the literature. Niels, I'm not sure if you will agree that I've gotten part of what you've said correct. I hope so. So in any case, I think these, what's interesting about these is that they each reflect a very different angle on the realism question, right? So I think, you know, if you think of realism as a question of ontological commitment to entities, then you might need a full characterization of that entity before you would say, this is something that I could be a realist about. Alison is interested in whether you have canonical empirical confirmation in a very precise sense, and whether you can have a realist commitment if you lack that, right? And he's worried that in a lot of cases in frontier physics, we don't have that kind of canonical confirmation. So what kind of stance should we take in that case? And there's a common thread among these. I won't mention the other two just for sake of time, but there's a focus on sort of semantic or epistemic prerequisites for realism or realistic commitments. And we can maybe go into this in more detail because I don't need to characterize your position because you're here. So there's the contrast between a very specific concept. If we had a particle physics candidate, imagine that you had a particular proposal for a WIMP that was the candidate for dark matter. I think on your account, that would then be a specific entity, but we can't be committed to it because there's massive underdetermination. So it would be, it wouldn't be natural to be a realist about that. But on the other hand, the common core, something like what I've characterized as just the cosmologically relevant properties of dark matter, is so semantically thin, so vacuous that it barely means anything at all, right? I think I'll skip a little bit here. So the approach I'm taking is really meant to show that we can focus on what it is that's actually relevant to successful measurement practices and what can support an iterative approach to understanding the phenomena. So rather than thinking, is the concept thick enough or do we have canonical detection, the question I'm focusing on is what features of dark matter are constrained by different measurements, and do these results converge and support ongoing inquiry in an appropriate way? And what I'm calling a measurement realist would be committed to the properties. What I mean by modal properties is sort of the counterfactually robust properties of the entities who've characterized it. But these can be limited to quite a partial account, right? There's no demand that you have a comprehensive account, and they can be scale dependent in the sense that we have a clear assessment of the properties of dark matter that are relevant on a cosmological scale, but maybe not at the microscopic scale or particle physics scale. So let me come back to the guiding questions. So I would argue, here I'm following Peebles, and I think it's the sort of consensus view among most cosmologists, that there has been substantial convergence on understanding the bulk properties of dark matter. But really constraints on underlying candidates, specific particle physics candidates or other candidates for dark matter, are still prospective. We don't have really much to say about what the underlying features of dark matter would be. And what the shift was in the early 2000s was an increased strengthening of that case, that the bulk properties of dark matter, we can now see dark matter being manifested in a lot of different ways, and that gives us more convincing evidence that the bulk properties are what we have described. The convergence on different features, we really have a set of core features: the overall density, the fact that it's non-baryonic, that it's collisionless and dissipationless. Those are the features that are relevant for how dark matter works in cosmological applications, and it seems like we have strong converging evidence for those. And there's convergence at cosmological scales, but as I said, there's very weak convergence at other scales. So we don't have the same kind of characterization of what the underlying particle physics constituents would be. So again, there's the same contrast. We have strong modal commitments with regard to the bulk properties, but not for the underlying physics. So to conclude then, so I've argued that we can think of the content of theories in terms of the way they support measurement practices. And when we have convergence of multiple independent measurement results, and that is maintained under increasing precision, we can take those results as a basis for further inquiry. That's a strong line of evidence to support taking those as the basis. In the case of dark matter, we have convergence on bulk properties. In some sense, we have like an effective ontology at cosmological scales. This has been foundational for cosmology, for the account of structure formation, for the precision measurements that were developed in the early 2000s. But that is contrasted with really weak constraints on the underlying candidates and accounts of what the particulate nature of dark matter might be. And so in terms of the sense in which this is a realist position, so I think a lot of people might hear this and think that it's really just instrumentalist, right? I'm really just some version of an instrumentalist. I want to say that it's not merely instrumentalist, because I think there's bulk properties have some kind of genuine ontological status. They're not merely treated as counterfactual devices. This is what I've been saying earlier about modal properties, that you can still do all kinds of counterfactual reasoning about if you have dark matter present and those have modal force. And it's expected to survive in the sense that most cosmologists would take it as a constraint on future theorizing that the current results about dark matter would be preserved in some sense in further theories. By contrast with a different approach, which takes entity realism as the appropriate way of framing this debate, first of all, I should just say I've been influenced by Howard Stein in this. I'm pretty skeptical of sort of reference-focused formulations of realism, where we ask, can we refer to an entity, and should our realist commitments follow that reference? I just don't know that that's the best way of posing the question about realism. And again, as opposed to some versions of entity realism, I just don't think we need a comprehensive characterization of dark matter or to find its kind constitutive properties and other things in order to have a commitment to it. And so I'm much more comfortable being committed to some kind of effective ontology, where that might be a partial account of dark matter, it might be scale dependent, but it's still, I think, a realist commitment. So it's much weaker than, it doesn't sort of meet the demands of entity realism, but I think it's still a realist commitment nonetheless. Okay, so just finally, the two open questions I started with: what does convergence contribute? So convergence provides mutual support for the linking assumptions when the methods contain constrain related features of the target system, so they're both bearing on the same thing, and they can enable further inquiry, and you hope that you'll continue to have convergence. And so for dark matter, convergence, I argue, has been achieved for bulk properties. And finally, what is the nature of the commitment to dark matter that's appropriate given our current situation? I think we have a variety of successful converging measurements, and so they're very strong for cosmological bulk properties, and they just give us really weak constraints on the underlying physics. But I still think of this as leading to genuinely realist commitments, not merely instrumentalist, but they're open-ended in a way that I think is appropriate. Okay, thank you very much.